During the last 6 months of 1965, facilities construction continued at the Manned Spacecraft Center in support of manned mission objectives. The 7-story project engineering facility was 77% complete. Exterior construction neared completion on the Lunar Mission and Space Exploration Facility. And beneficial occupancy was achieved in major portions of Building 14. Testing programs in Building 14's laser laboratory are helping perfect space-to-ground optical communication systems. The television signal is transmitted in a light beam generated by a low-energy helium-neon laser. An anechoic chamber, also in Building 14, was turned over by the contractor late in the year. The chamber will be used to qualify Apollo spacecraft communication systems. The protruding structures absorb electronic echoes, giving the chamber a non-reflective quality similar to space. A 55-foot high door can be rolled back, enabling the chamber to be used with transmitter and receiving equipment located on the outdoor antenna range. The range was also completed during the reporting period. Electromagnetic energy of a different sort will be studied by a solar particle observatory completed at the Manned Spacecraft Center in November. The observatory will be part of a 3-station network that will warn of impending solar flare activity. Radiation from such solar disturbances could endanger astronauts on a lunar mission. Equipment for lunar missions will receive advanced testing in MSC's 35-foot altitude chamber, which passed its man-rated test in December. The test subject, wearing a modified Gemini extravehicular pressure suit, spent 11 minutes in a simulated 300,000-foot altitude. The walls of the chamber were cryogenically cooled to minus 270 degrees Fahrenheit. Quartz lamps simulated 270 degrees solar heating. In the area of flight crew training, a number of simulation devices were introduced at MSC. A multiple target display system was activated by the Flight Crew Support Division for use with the Gemini mission simulator. Targets, such as this 1/5 scale Agena docking vehicle, are photographed by a television camera and projected at the windows of the Gemini mission simulator. In addition to star fields, the system is capable of displaying an Earth model. The TV camera photographs the model from a simulated altitude of about 100 miles. More realistic flight crew training is possible with a dynamic crew procedures trainer. High-fidelity speakers, vibratable pilot seats, and space environment projectors provide audible, kinesthetic, and visual cues simultaneously. Earth, star field, and rendezvous light images are projected on the inside of the 40-foot diameter shell, which surrounds the crew station. Crew stations can be quickly interchanged, making it possible to support Gemini and Apollo programs concurrently. By the end of December, the Link Group, Binghamton, New York, completed installation and checkout of the Apollo mission simulator. It will be the most complex training aid used at MSC. The device employs a realistically configured Apollo command module mock-up for simulating spacecraft performance and flight dynamics. Optical display units project the desired flight conditions through the spacecraft windows and optical systems. Artwork for the displays was being executed by the Wilding Company, Chicago. The detailed Earth renderings are photographed with aerial mapping equipment. The film rolls are spliced to provide a continuous picture of the Earth's surface as it would appear from an orbiting spacecraft. At NASA's Langley Research Center, Hampton, Virginia, another type of simulator was put into service. Called a Lunar Landing Research Facility, the simulator includes a 250-foot-high framework and a research vehicle which can simulate the weight and flight characteristics of the lunar module. Flight profile simulations will be flown to study control devices and control characteristics, pilot visibility, and instrumentation needs. While primarily an engineering simulator, the facility will be available for advanced astronaut training in lunar landing procedures. The facility is representative of a number of fundamental research projects being conducted by Langley in support of manned spacecraft programs. Astronaut training included continued geology studies at lava fields in Iceland, Alaska, and Mexico. The training is designed to acquaint astronauts with geological features they may encounter on the Moon, and to help them select the most meaningful samples for later study on Earth. The first class of scientist astronauts began flight training at Williams Air Force Base, Arizona. The course is designed to provide experience in high-performance aircraft and flight dynamics. Classroom sessions were followed by training flights in supersonic aircraft. MSC continued manned mission support in a broad area of development activities. For example, the Crew Systems Division introduced a new soft-wear pressure suit. The suit was given its first practical test by the Gemini 7 flight crew during a spacecraft altitude checkout. The suit provides greater comfort during long-duration missions. All suit components were thoroughly tested before being flight qualified. The hood assembly successfully withstood a 500-mile-per-hour wind blast, equivalent to the wind force that would be exerted during an astronaut abort ejection from the spacecraft. Engineering models of the Apollo lunar mission pressure garment and backpack were also introduced. The units are part of the Apollo Extravehicular Mobility Unit, which includes a water-cooled undergarment, the pressure garment assembly, the portable life support system, or backpack, and a thermal micrometeoroid protection garment. An extravehicular visor assembly attaches to the helmet. The tinted visors can be used singly or in combination. A developmental hard suit for the Apollo Applications Program was also introduced. The aluminum and fiberglass suit will aid astronauts in carrying out a proposed schedule of extended lunar surface investigations. MSC received the charter to perform spacecraft integration and modification work for the Apollo Applications Program. Space tools are also being developed. This battery-powered zero-reaction tool was built for the Air Force by Black & Decker under subcontract from the Martin Company. The tool will receive its first space test during the Gemini 8 mission. Other development programs were being conducted by MSC's Advanced Power Systems Laboratory. SNAP-13 radioisotope thermionic generators are being studied as spacecraft or space station electrical power sources. Additional power sources being investigated include internal combustion engines, seemingly ordinary in principle, but fueled with hypergolic propellants. Such an engine, using propellants left in the tanks of a lunar module descent stage, would power a conventional electric generator. Other MSC development efforts were directed to perfecting spacecraft recovery hardware. Simulated Apollo pad abort recovery tests were conducted in the Gulf of Mexico off Galveston, Texas. A Marine Corps amphibious vehicle was employed using a recovery crane designed by the Landing and Recovery Division. A reef around the Cape Kennedy launch area prevents the use of deeper draft vessels. Recovery personnel were also involved in the problem of spacecraft righting techniques. Under certain conditions, as demonstrated in the North American pool at Downey, California, the spacecraft can hit the water with its leading edge with undesired results. To upright an overturned spacecraft, a flotation bag system was developed. System qualification tests began late in the reporting period. Pararescue training was also conducted by MSC personnel to develop delivery techniques for the Apollo flotation collar. The results of gravity drops and parachute drops will be compared to determine the best delivery method. Evaluations will be made on the basis of drop accuracy and minimum damage to the collar. While encompassing extensive in-house development programs, MSC efforts continued in the major areas of developing operational manned spacecraft and their mission control capability. In the Gemini program, the first mission of the reporting period was Gemini 5. Astronauts Gordon Cooper and Charles Conrad were launched from Cape Kennedy on August 21st. Primary objective was to accomplish an 8-day mission. The objective was achieved as planned. Eight days later, the flight crew was recovered by the carrier Lake Champlain. The mission provided the first evidence that man could function during prolonged spaceflight and that the Gemini spacecraft was a valuable scientific platform capable of supporting even longer missions. After Gemini 5, manned flight progress hinged on the rendezvous flight of the first Agena target vehicle and the Gemini 6 spacecraft. Thorough ground testing and a record of almost 90% success in nearly 200 launches of the parent Air Force Agena vehicle led to verification of the target vehicle without a flight test. The Atlas Agena target vehicle was launched from Cape Kennedy on October 25th. Although the Atlas performed perfectly, the Agena malfunctioned and failed to achieve orbit. Top priority has been given to modifying the remaining 5 target vehicles to ensure their performance on the final Gemini missions in 1966. Loss of the target vehicle canceled the Gemini 6 mission. Astronauts Walter Schirra and Thomas Stafford were to have rendezvoused and docked their spacecraft with the target vehicle. To offset a threatened program delay, NASA instituted a series of rapid schedule and mission revisions. Gemini 6 was de-erected, and Gemini 7 was erected in its place. Frank Borman and James Lovell, wearing the new lightweight pressure suits, were the flight crew for Gemini 7. Primary mission of the flight: to evaluate the capabilities of the flight crew and spacecraft during 14 days of weightless flight. The spacecraft would also serve as a target vehicle for Gemini 6. On December 4th, 6 weeks after the target vehicle failure, Gemini 7 rose from the Kennedy Space Center's Launch Complex 19. Within 24 hours after Gemini 7 was launched, Gemini 6 was erected at Launch Complex 19. 8 days after Gemini 7 left the pad, Gemini 6 was ready for launch, completing a record pad turnaround 1 day ahead of schedule. On December 12th, the countdown for Gemini 6 reached 0. The engines ignited, burned for almost 1.5 seconds, and shut down. A pull-away checkout plug had prematurely dropped from the vehicle, causing engine shutdown. 3 days later, astronauts Schirra and Stafford again entered the Gemini 6 spacecraft. On December 15th, the third launch attempt for Gemini 6 was successful. The mission to rendezvous with Gemini 7. Guidance to the vicinity of the target would be by ground-based computer data gathered from worldwide tracking reports. Rendezvous was accomplished approximately 6 hours after the launch of Gemini 6. During subsequent inspection and station-keeping exercises, the spacecraft were flown to within 1 foot of each other. Had there been a docking ring on either spacecraft, a physical link-up would have been possible. For the Mission Control Center, Houston, the flight proved a capability to direct and bring together 2 spacecraft at a predetermined point in space, a capability that will be essential to the Apollo lunar mission. Gemini 6 re-entered December 16th. Gemini 7 followed on December 18th. The spacecraft were the first to come in under controlled re-entry. Both landed less than 10 miles from their predicted impact points. The accuracy of the landings demonstrated the feasibility of controlled re-entry for Apollo. Both spacecraft were recovered by the carrier WASP. All objectives of the Gemini 7 and 6 missions were accomplished. For example, the Gemini 7 crew completed the longest manned spaceflight on record, giving the United States an additional 330 hours of manned spaceflight experience. All experiments were performed satisfactorily, including the first use of star sightings to align a spacecraft. The experiment proved the value of celestial navigation as a backup to a spacecraft's inertial guidance system. The flight was also the first in which the flight crew flew much of the mission in a shirt-sleeve environment. The soft suits permitted the crew to remove and stow the garments with relative ease. Of medical importance was the fact that the flight crew remained alert and performed efficiently throughout the 14-day mission. More significantly, post-flight medical examinations demonstrated that the astronauts had no inhibitive physiological effects. Overall, the Gemini 7 and 6 missions demonstrated a growing precision and flexibility in manned spaceflight operations. Remaining Gemini missions will concentrate on increasing operating proficiency. The first of the 1966 missions will be Gemini 8, scheduled for March. In late October, the Gemini 8 spacecraft was in simulated flight testing at the McDonnell plant in St. Louis. The target docking adapter, which will be used on the mission's Agena target vehicle, was tested concurrently to ensure systems compatibility. A transponder mounted in the extended boom will amplify and return the spacecraft's radar signals during rendezvous operations. The Gemini 8 primary flight crew, Neil Armstrong and David Scott, participated in an altitude test of the spacecraft. The test validated the environmental control system and other key spacecraft functions. In further preparation for the Gemini 8 mission, astronaut Scott practiced extravehicular activity aboard an aircraft flying parabolic trajectories. During the Gemini 8 mission, Scott will leave the spacecraft cabin and work his way to the rear of the adapter section. There he will strap on the extravehicular support package before commencing a 90-minute excursion around the spacecraft. Meanwhile, astronaut Charles Bassett trained with a model of an Air Force astronaut maneuvering unit he will use during Gemini 9 extravehicular activity. The backpack is mounted on a frictionless air-bearing platform which responds freely to the unit's thrust impulses. The flight model maneuvering unit, built by Ling Tempco Vought, passed acceptance tests at McDonnell before being installed in Spacecraft 9's adapter. Thrusting is achieved by firing hydrogen peroxide bursts through a series of directional nozzles. MSC-directed efforts showed continued manufacturing progress in the Apollo program. At North American's Downey plant, the propulsion module for spacecraft O-11, the second unmanned Apollo spacecraft, completed proof and leak testing. In the North American clean room, a growing number of ground and flight test spacecraft were in the final stages of systems installation, including the command and propulsion modules for spacecraft O-12, the first manned Apollo spacecraft. The spacecraft is scheduled for shipment to Cape Kennedy in mid-1966. The command module for spacecraft O-14 was in wire harness installation in preparation for systems installation. The spacecraft is slated for the second manned Apollo mission. At North American's Tulsa facility, separation tests were begun on the lunar module's adapter section. In space, the panels will be blown back to allow removal of the lunar module from the adapter. In December, the lunar module adapter section for the first Apollo uprated Saturn I flight was prepared for helicopter delivery to Cape Kennedy. The trip from Tulsa to the Cape took approximately 24 hours. At Grumman's Bethpage, Long Island plant, the first flight article lunar module entered structural assembly. The module will be flown in an unmanned test aboard the sixth uprated Saturn I launch vehicle. Ground test articles were also in final assembly at Bethpage. Test Article 8 will be shipped to the Manned Spacecraft Center for thermal vacuum testing. Propulsion Ascent Stage Number 2 is destined for hot firing tests at NASA's White Sands Test Facility. Lunar module engine development continued with test firings of the ascent engine at Bell Aerosystems and firings of the descent engine by TRW. The engines were also fired at the Air Force's High Altitude Test Facility, Tullahoma, Tennessee. The Aerojet propulsion module engine was also tested under high altitude conditions at Tullahoma. On July 1st, the engine nozzle failed during a developmental firing. The problem was corrected before the start of qualification testing for the first Apollo uprated Saturn I mission. At NASA's White Sands Test Facility, propulsion subsystem qualification tests for the first Apollo mission were completed on October 25th. The tests, using a nozzle skirt simulator, duplicated the firing programs that will be followed on the first Apollo mission. Spacecraft 009 modules for the first Apollo uprated Saturn I mission arrived at the Kennedy Space Center in October. The propulsion module was transported to the propulsion test facility at Complex 16, where pre-flight checkout programs were conducted, including a propulsion subsystem firing. While the propulsion module was undergoing static tests, the command module underwent electrical power and instrumentation checks at the hypergolic test facility. Following cleaning and build-up, the mated command and propulsion modules provided the first view of a fully configured flight article Apollo spacecraft. On December 26th, the spacecraft and the attached adapter section were mated to the uprated Saturn I launch vehicle. Tests began immediately in preparation for a launch early in 1966. In support of manned spacecraft programs, government and industry continued unmanned space investigations. In late summer, a dummy model of the Surveyor spacecraft was prepared for launch aboard the 6th Atlas Centaur launch vehicle. Future Surveyor spacecraft will soft land on the Moon and conduct lunar surface studies in support of manned Apollo operations. The Surveyor program is managed by the Jet Propulsion Laboratory under the direction of NASA's Office of Space Science and Applications. The second stage Centaur is being developed by NASA's Lewis Research Center. On August 11th, the vehicle successfully injected the dummy spacecraft into a simulated translunar trajectory. The maneuver will be critical to the success of operational Surveyor missions. In July, the Mariner 4 spacecraft, also developed by the Jet Propulsion Laboratory, transmitted the first close-up photographs of the planet Mars. The photographs provided study data for possible future manned missions. In addition to furthering government research efforts, manned spacecraft programs help stimulate corporate-funded research into broad areas of applied science. Scientists of the Aerojet General Corporation, for example, are using rock samples of a type which are believed available on the Moon in experiments to produce water. Water can be electrolyzed into hydrogen and oxygen. Oxygen can help support life in space, or hydrogen and oxygen could be liquefied for use as rocket engine propellants. Several companies are experimenting with lunar exploration vehicles. Grumman, in a company-funded development project, built this full-scale operating vehicle using a company-patented wheel design. While MSC achievements in the last half of 1965 were milestones in building an operational manned spacecraft capability, they also encouraged the growth of fundamental knowledge that can be used equally well in unlocking the mysteries of space or in improving the condition of man on Earth.